So now that we've looked at the proof for the fundamental theorem of calculus, we can look at how we can use the differential form to simplify some expressions without having to do a whole heap of work. Now the differential form just means this form that has d dx at the front. So it means differentiate this integral, and what you'll get is actually just the function itself. Now you'll notice that here our upper bound is x, and what we get is the function of x. So in these couple of examples, you'll see that it's really quite straightforward to just follow this formula and say that if we are differentiating this integral, then actually what we'll just get is f of x, not f of t, but f of x. So we'll end up just with the natural log of x. Now this is pretty handy because this one, we couldn't have actually evaluated the integral because we haven't looked at how to integrate y equals the natural log of x, or t for that matter. So to integrate this and then differentiate it would have been tricky, but to use this shortcut makes our life really easy. For this one, we can see that this is the function itself, that's the function of t. So if what we're going to get is the function of x, we just use that exact formula there, but put x's in where the t's were, and that's our solution. Now, I've written here that there's no need to actually evaluate the integral and then differentiate it because we've got this shortcut. If we're differentiating a primitive, and here what we can see is that this is differentiating an integral, then what we're going to get is just little f of x, so we get the function itself. Now if you want a very quick proof as to why this lower bound here doesn't matter, let's just have a look at a more simple example, one that we easily can integrate and then differentiate. Let's say we were doing one like, say, from 4 up to x, and we just had t squared dt. All right, if we did it the fast way, we'd say, look, we're just going to get x squared. But let's do it the slow way just to see what would have happened. And we'll say that we're going to need to d dx t cubed on 3. So I've just found the primitive of t squared there. And my bounds are x and 4. So then I'd need to d dx x cubed on 3 minus 4 cubed on 3. Now when we differentiate something with two terms, we can do it just one term at a time. So differentiating this means I need to bring the 3 down. It's going to cancel with that 3, and the 3 is going to drop down to a 2. I'm just going to get x squared because differentiating a constant gives me nothing at all. So sure enough, that's exactly what I get. Now if I was to change this bound, what if it was something like 3? It's not going to make any difference whatsoever because what I'm going to get over here is still going to be a constant, and differentiating that gives me nothing at all. Now we'll have a go at proving the integral form of the fundamental theorem. Now this is the form that you've already been using every single time you find a definite integral. It's the one that says that if f of x is some continuous function in this interval between x equals a and x equals b, and big f of x is a primitive of that function, then we can say that this notation, which tells us that we want the area underneath the curve from the lower bound of a up to the upper bound of b, is equal to big F of b minus big F of a. Now you've already been using this and you've just taken it for granted that it works. Now is our chance to actually prove it. Now we're proving it based on what we just did when we proved the differential form of the fundamental theorem. We can use that in this proof. So to prove it, we already saw that if we differentiate big F of x, in other words we find big F dash x, what we get is just little f of x. So that means that big F of x is a primitive of f of x. But we also know that this notation here is equal to big F of x. So if big F of x is a primitive of little f of x, and big F of x also equals this, then this stuff must also be a primitive of little f of x. Does that make sense? Now, we've already seen that any two primitives of a function only differ by a constant. So if we take this one here and say that it is equal to this other primitive plus some constant, whatever that might be, then we can start to work with it. Now the trick to this proof is letting a equal x. You'll notice that a is our lower bound, x is our upper bound. But as soon as we sub in a for x, what we get is an integral that actually has 0 width. We've got an integral from a up to a, so in other words, it has no area at all. So if we say that this integral equals 0, then we have 0 is equal to big F of a plus c. So if we want to know what C is, we would just get C on its own here and say C is equal to the negative big F of little a. Now how does this help us? Well, back here we've got an expression for this integral, right? We've said it's big F of x plus C. And now we can say, hey, we know what C is. It's negative big F of a. So subbing that in here, I can write a new version of this where we had all of this is equal to big F of x minus big F of a. Okay, now this is almost looking like what we have up here. The only difference is that here we've got big F of b rather than x, and here we've got a and b as our bounds, not a and x. Well, if x is the upper bound, and that goes here, and here b is the upper bound, and that goes there, then we can literally let x equal b, and we can also let t equal x. Now, why are we doing that? Well, instead of having our variable x being one of the bounds, we're just making it be in the actual function. Really just fiddling around with the letters. But what we're going to get is the exact thing that we want, which is a to b of f of x dx must be equal to the big F of the upper bound minus the big F of the lower bound. And we have the proof here, which is really quite straightforward. Now, this part of the proof is not necessarily something that you need to reproduce in exam conditions, but it makes sense to be able to follow it through and to understand why we're using the formula that we're using.